Welcome to day 15 of our 15-day beginner data science sprint. We made it to the final day. Over the last 14 days, we learned Python, NumPy, Pandas, data cleaning, visualization, exploratory data analysis, statistics, machine learning, regression, classification, evaluation, and model improvement. But knowing these things individually is not enough. A real data science project requires us to connect them. So today, instead of learning one new technique, we are going to build an entire project from beginning to end. We will start with a CSV file. We will understand it, clean it, explore it, define a machine learning problem, create a baseline, build a better model, evaluate that model, and most importantly, explain what we learned and what our model cannot tell us. By the end, you will have a notebook that can become your first portfolio data science project. Let me start with a question. Imagine someone sends you a CSV file containing information about students. It contains things like study hours, attendance, previous scores, sleep, participation, and final scores. Can you take that raw CSV and turn it into something that could actually help someone make a decision? That is what a data scientist is expected to do. The final model is only one small part of that process. A strong project tells a coherent story. We should be able to explain what problem we are solving, what data do we have, can we trust the data, what patterns do we observe, what should we predict, how good is our prediction, what mistakes does our model make, and what should someone not conclude from our analysis. Today, we will answer all of these questions. Our project will be called Student Success, identifying students who may need early support. Our main question is, can we use information available before the final examination to identify students who may be at risk of a low final score? Notice the wording. We are not trying to label students as good or bad. We are not trying to automatically punish or rank anyone. We want to identify students who may benefit from additional support. That distinctions is important. Now, this might look like documentation rather than data science, but documentation is part of data science. If somebody opens your GitHub project 6 months later, they should understand the purpose before reading a single line of Python. Now let's import our libraries. We are simply loading the tools that we will need later. And notice something important. We are using libraries that appeared throughout this series. Pandas, NumPy, Matplotlib, Seaborn, and Scikit-learn. Today we connect all of them. Let's load our student success dataset. Now inspect the first few rows. Before running the next cells, predict what each one will tell us. This tells us how many rows and columns we have. This tells us the column names, data types, and missing values. And this gives us numerical summaries. You should never jump directly from read CSV to machine learning. First, understand what you are working with. Let's document our important variables. Your exact dataset may contain a few additional variables. That is completely fine. A data dictionary makes your project much easier for another person to understand. Now we start asking whether the dataset is reliable enough to analyze. First, missing values. So there are some missing values like study hours, there are 13 missing values and so on. Now duplicate rows. So there are 5 duplicate rows. And let's inspect our numerical ranges. Suppose attendance suddenly contains a value of 250. That should immediately make us suspicious because attendance expressed as a percentage should normally not exceed 100. The computer does not automatically understand what values make sense. Domain knowledge still matters. Let's remove exact duplicates. Notice that we are not immediately filling all missing values. Why? Because later we will put missing values handled inside our machine learning pipeline. That makes the workflow safer. Our final score is numerical, but our decision support question is which students may be at risk. For this project, we will define a student as at risk when final score is less than 50. Let's create the target. Now examine the target and percentages. Remember, day 12 and day 13, class balance matters. If only 10% of students are at risk, a model could predict not at risk almost every time and still achieve 90% accuracy. That is why we cannot judge classification using accuracy alone. Before building the model, let's understand the data. First, the final score distribution. Now describe what you see. Do not immediately explain why it happened. That distinction is important. Observation comes before explanation. Now let's inspect attendance. If at risk group appears to have lower attendance, we can say students classified as at risk tend to have lower attendance in the dataset. But we should not say low attendance causes students to fail. Our chart shows association, it does not prove causation. Let's do the same for previous scores. Again, ask yourself what relationship do you expect? Then run it. Let's inspect correlation. Remember, a correlation close to 1 suggests a strong positive relationship. A correlation close to -1 suggests a strong negative relationship. A correlation close to 0 suggests linear relationship. But correlation still does not prove causation. Before continuing, stop the video for a moment. Choose the single most important chart we have created so far. Now explain it in one sentence without using words such as correlation coefficient, distribution, variance, regression, or statistical significance. Imagine you are explaining it to a school teacher. For example, students are already had lower previous scores appear more likely to need additional academic support. That is the communication skill we are practicing. Now let's build our model. We will use information that could reasonably be known before the final examination. Notice what is not inside X, final score. Why? because final score was used to create our target. If we include final score while predicting whether final score is below 50, we would give the model the answer. That is the data leakage. And it would create a model that looks excellent but is useful to the real world. Now split the data. Why do we use stratify equal to y? Because we want approximately the same class proportions in our training and testing data sets. Let's check the sizes. Before building something sophisticated, we need something simple to beat. That is our baseline. We will use a classifier that simply predicts the most common class. Now evaluate it. Something interesting may happen here. Our baseline accuracy might not look terrible, but its recall for at-risk students could be extremely poor. Possibly, like you can see 0. Think about what that means in plain English. The model may achieve reasonable accuracy while completely failing to identify the students we actually care about. This is exactly why choosing the correct metric matters. Now let's create a better workflow. We will build a pipeline containing these three steps. First, fill missing values. Second, scale the numerical features. Third, train logistic regression. Why use a pipeline? Because pre-processing should be learned using training data only. The pipeline helps prevent accidental leakage. And why have I added class weight equal to balanced? Because if our at-risk class is smaller, this tells logistic regression to pay more attention to class imbalance. Now train the model and create predictions. Let's calculate several metrics. Do not immediately ask, is the accuracy high? Instead ask, what mistakes matter? In our use case, missing an at-risk student could be important, so recall deserves particular attention. High recall means of the students who were actually at risk, what proportions did our model successfully identify? Now print the full classification report and create the confusion matrix. Pause here. Can you identify true negatives, false negatives, true positives? For this project, pay particular attention to false negatives. These are students who were actually at risk but whom our model failed to identify. A machine learning metric represents real mistakes. That is something you should always remember. Our test results came from one particular train test split. Would we get approximately the same result with another split? Let's use cross validation now. Evaluate several metrics and summarize them. This is more informative than relying on one lucky train test split. If performance changes dramatically between folds, that is something we should investigate. Cross validation doesn't guarantee that the model will perform perfectly in the real world. It simply gives us a more stable estimate using the data that we currently have. Let's Put our results into a simple table and visualize the difference. And ask yourself, did our improved model actually improve the metric that matters? That is much more important than saying I used logistic regression. Machine learning is not algorithm shopping. Our goal is to solve the problem better. Now we reach one of the most important parts of the project, the findings. A portfolio project should not finish with F1 is equal to 0.78 and stop there. A non-technical reader should understand what you learned. Our key findings are previous academic performance appears strongly related to final performance. Students in the at-risk group generally show lower attendance in the dataset. Study behavior and participation provide additional information that can help identify potentially at-risk students. The improved classification model performs better than the simple baseline, particularly in the identifying students who may need support. Model predictions should be used to trigger further human review or assistance rather than automatic academic decisions. Your exact findings should be depend on your output. Do not copy conclusions that your data doesn't support. This is where many beginner projects become unrealistic. They show impressive graphs and metrics and then act as through the project has solved education. It has not. Add a limitation section also. The dataset may not represent students from different institutions, regions, or educational systems. Relationships in the data do not establish causation. Important factors such as teaching quality, family circumstances, health, motivation, and access to resources may be missing. Model performance on this dataset does not guarantee equal performance on future students. The definition of at-risk using a score below 50 is a simplified project definition. Predictions should support human decision making rather than replace it. If you are using the synthetic student success dataset created for this tutorial series, add. Also, this project uses a synthetic educational dataset created for learning purposes. Results should therefore be treated as demonstrations for the data science workflow rather than real educational evidence. That sentence makes your project more credible, not less credible. Being honest about your project data is a strength. We should also think about how a model like this could be misused. This is a part of responsible data science. Now I want you to complete the learner evidence for day 15. Write one sentence explaining the most important result. For example, information available before the final assessment helped our model identify many students who may need additional support. Although the predictions are imperfect and should be reviewed by people, notice what this sentence does not contain. No F1, no logistic regression, no cross validation, no scikit-learn. It explains the meaning. Now it's your turn. Your challenge is not to train another algorithm. Your challenge is to turn this notebook into a reproducible portfolio project. Complete these tasks. Finish every notebook section. Replace generic observations with findings from your actual outputs. Add a limitation section. Add the one sentence interpretation, create a GitHub repository, upload the notebook, upload the dataset if redistribution is allowed, add a README file, ask another person to open your project and run it from the beginning. Here's the important test. If your friend cannot understand how to run your project is not reproducible. Now, creating the README file, your repository might look like this. Your README can contain this: tools, workflow, running the project, main finding, and limitations. And if you want to create a basic requirements.txt, you could use this. You do not need a complicated repository. Clarity is more important. Now send the GitHub repository to someone. Do not explain how it works. Do not explain how it works. Ask them, can you run this project from the beginning and tell me where you get confused? This is an extremely useful test. Maybe your dataset path is unclear. Maybe the README does not explain what the project does. Maybe a cell depends on something you ran manually earlier. Maybe the notebook has 20 unnecessary cells. These problems matter. A portfolio reviewer is not evaluating only your model. They are also evaluating your how you think. The biggest mistake I want you to avoid today is this: building the entire project around model accuracy. Suppose a candidate says, my model achieves 89% accuracy, and candidate B says, my model improves recall over the baseline, but false negatives remain important. The dataset is synthetic and excludes several factors that affect student performance, so the model should only be considered a demonstration of an early warning workflow. Candidate B sounds much more like a data scientist. A model score, a model score is evidence. It is not the entire project. Let's recap. On day one, we asked what is data science. Today, you should have a much cleaner answer. Data science is not importing pandas, making colorful charts, or calling dot fit. It is a process. We start with a question. We understand the data. We check its quality. We clean it carefully. We explore patterns. We separate observations from explanations. We define inputs and targets. We create a baseline. We train a model. We evaluate the mistakes, improve the workflow without leaking information. We communicate what the results mean, and we clearly state that what do not what they do not prove. That is the workflow you have practiced throughout the 15-day series, and the most valuable thing you gained in is the knowledge of a particular algorithm. It is the ability to look at a data set and know what questions to ask next. Before finishing the series, answer these two questions without looking at your notes. First, what new capability did we gain today? A good answer would be, I can now take a dataset through a complete data science workflow and turn the analysis into a reproducible project. Second, what model output and limitations should you be able to explain without notes? You should be able to explain what your most important evaluation metric means in plain language and describe at least one reason why the model may not generalize perfectly. If you can do that, you are no longer just copying Python code. You are beginning to reason like a data scientist. And that completes our 15-day beginner data science sprint. In 15 lessons, we moved from understanding what data science actually is to building an end-to-end machine learning capstone project. Do not stop here. Take this notebook, improve the README, change the dataset, try a different question, add another model, compare results, and most importantly, keep asking, What does the output actually mean? Because tools will change, libraries will change, AI will write more code for us, but the ability of frame the right problem, analyze evidence carefully, and communicate a trustworthy conclusion will remain valuable. Congratulations on completing day 15 and the entire data science sprint. Now publish the project and turn what you learned into something that other people can actually see.